We've all used the calculator apps on our computers and mobile devices to add and subtract numbers. But many people do not realize that these devices approach these operations in a fundamentally different way from the way humans approach them. In this video, we'll go over how computers represent numbers and perform these arithmetic operations on them. Me personally, I found the way that computers subtract numbers to be very fascinating, and I hope you will too. We humans use the decimal system, the numbers 0 through 9, 10 in total, to represent all imaginable numbers. Computers use a different system called the binary system that uses only two symbols, 0 and 1. Let's look at a side-to-side comparison between decimal and binary to see how we can use these two symbols to represent all numbers. Obviously, 0 and 1 look exactly the same. The problem arises when we want to represent 2 in binary, because we already ran out of symbols. The way to approach this is to think about what we do when we want to represent 10 in decimal. So when we get to 9, we introduce another digit, set it to 1, and set the previous digit to 0. Well, in binary, since we already reached our maximum symbol, which is 1, we'll do the same thing. We'll introduce another digit, set it to 1, and set the previous digit to 0. So 2 in binary looks like this, 1, 0. 3 in binary is 1, 1. To represent 4, we'll need to think about what we do when we get to 99 in decimal. Since we got our maximum symbol at 2 digits, we'll introduce a new digit, set it to 1, and set the previous digits to 0. So 4 is 1, 0, 0. 5 is 1, 0, 1, and 6 is 1, 1, 0. There are some parallels we can draw between the decimal and binary system. For example, if we look at the number 309, we know that these symbols represent the units, tens, and hundreds. So this number has 3 hundreds, 0 tens, and 9 ones. In binary, however, it is a bit different. So if we look at a number like 1001, those numbers do not represent units, tens, and hundreds. They represent units, twos, fours, and eights. And if we keep going, it would be 16s, 32s, and so on, which are the powers of 2. This number has ones at the eights and units places, so we can calculate what that number is by doing 8 plus 1, which is 9. So 9 in decimal is equivalent to 1001 in binary. The reason why computers use the binary system instead of, let's say, the decimal system is because computers are built on transistors. These transistors can exist in two states, on and off, which can be used to represent the 0 and 1 in the binary system. Now let's move on to addition in binary. So first we'll look at how humans can add numbers in the binary system. So let's look at this example, which is 0111 plus 0011. If we look at the places of these ones, this addition represents 7 plus 3, which should come out to 10. So the way we do this addition is the way we do it in decimal. So we first look at the first 2 bits and we add them. So 1 plus 1 is 2. 2 in binary is 1, 0. So the way we move forward is by putting the 0 down in the answer and carrying the 1. Then we move to the next digits. So here we have 1, 1, and 1 in the carry. So this comes out to 3, which is 1, 1 in binary. So we put 1 in the answer and carry a 1. In the next digit we have 1, 1, and 0. So this is 2. We do the same thing. We put a 0 down and carry a 1. And in the last digit we have 1 and 2 zeros, which comes out to 1. So if we look at the places of the ones here, we realize that we have a 1 at the 8th place and a 1 at the 2nd place, which comes out to 10 as we expected. You might have noticed that we were repeating the same operation over and over again. For example, here we were taking 3 inputs and calculating 2 outputs. The inputs were the carry in from the previous stage, the 2 bits from the 2 numbers, and we were calculating the number that goes out in the sum and the carry out to the next stage. So we're going to give these inputs and outputs names. Here Cn for carry in, A and B for the 2 bits from the 2 numbers, S short for sum, and C out for carry out. So if a computer wants to perform addition of 2 binary numbers, it must have a way to calculate these 2 outputs from these 3 inputs. And this is what it does. Computers have a circuit called a full adder that takes these 3 inputs and calculates these 2 outputs. To understand how a full adder works, we'll need to take a small detour and talk about logic gates for a moment. Logic gates are the building components of a computer, and they are built from transistors. To build the full adder, we'll need 3 types of logic gates, which are the AND, OR, and XOR gates. This is what these gates look like. They all take 2 binary inputs and output 1 binary output. The AND gate behaves like this. It outputs 1 only when both its inputs are 1. The OR gate outputs 1 when at least one of the 2 inputs is 1. And the XOR gates outputs 1 when the inputs are different, so when one is 0 and the other is 1, and outputs 0 when the inputs are similar. If these logic gates are connected in this configuration, where the output of some gates are fed as inputs to other gates, this circuit will behave as a full adder. Try and follow this circuit and make sure that everything is correct. This is in fact the same example that we saw earlier. Also, experiment with different inputs and make sure that the output is always correct. So how can we use this full adder to perform addition of 2 binary numbers? Let's say we want to do this operation right here. Just as a reminder, this is what the full adder looks like. So first of all, we need to add these 2 digits. We're going to use the full adder and feed it A0 and B0. And because this is the first stage in the addition, we're going to set the carry in to 0. Using these 3 inputs, we can already calculate S0 here. The carry out of this full adder will be fed as the carry in to the next full adder, which will take A1 and B1 as inputs as well. This full adder will calculate S1 and the carry in to the next full adder. Same here, we'll calculate S2 and the next full adder will calculate S3. So here, because we represent numbers with 4 bits, we're going to need 4 full adders to calculate the 4 bits in the answer. Again, here we're assuming that we're using 4 bits to represent numbers. Computers do the same thing but with larger amount of bits. So in that case, if we get a carry out at the last full adder, we're not going to be able to represent the number with 4 bits. We're going to need a 5th bit to represent the number. And if we only have 4 bits allocated to represent numbers, then we have a problem. This is called overflow. Overflow basically means that we cannot represent the answer with the amount of bits allocated to it. Now, what about subtraction? Your first instinct might be to build something similar to the full adder that does subtraction. While this could work, that's not how computers do it. Computers utilize this adder circuit with some minor modifications to work as both an adder and a subtractor. But before we get into that, we're going to need to look at some math to see how we can use this adder to perform subtraction. To do so, we're going to make use of a mathematical trick that allows us to calculate the answer of a subtraction operation by only performing addition. What do I mean by that? Let's get back to the decimal system and look at an example. Let's say we want to calculate 77 minus 34, which should come out to 43. The trick here is to add 100 to both sides. This way, the right-hand side of the equation becomes 143, which looks like a 1 next to the answer we want, which is 43. So theoretically, if we ignore this 1, we can get to our answer. But how is this helpful? Well, if we look at the left-hand side and rearrange it this way, Now it looks like we're adding two numbers instead of subtracting. Well, you might say that we're still subtracting 34 from 100. Well, you're right, but if we do this trick, we'll only need to subtract numbers from 100 and not from any random number. So theoretically, if we find a way of getting the result of subtracting numbers from 100 without doing that much work, then we kind of solved our problem. It turns out that doing the equivalent of this in binary is very easy and simple. So let's see what that looks like in binary. Let's say we want to do 7 minus 3 in binary, which should come out to 4. In binary, instead of adding 100 to both sides, we add 16, because it looks like 1 with 4 zeros next to it. Now, the right-hand side will look like our answer with a 1 next to it. And if we rearrange the left-hand side like we did in the decimal example, it would look like we're adding these two numbers. So now the challenge becomes, how can we calculate this value? Well, this operation actually has a name. It's called taking the 2's complement of a number. And it is extremely easy to do, as it only involves two steps. The first is inverting all the bits. So here 0011 becomes 1100. And the second step is adding 1. So we get 1101. And this is the 2's complement of 0011. Notice that if we were representing numbers with 5 bits instead of 4, we would be subtracting from 32 instead of 16. But these two steps would remain unchanged no matter how many bits we're using to represent numbers. We can think of the 2's complement as taking the negative of a number. Since taking the 2's complement of 3, which is 1101, and adding it to 7, acted as subtracting 3 from 7. But 1101 is also 13. So what should we do? Should we think of 1101 as negative 3 or as 13? Well, it turns out that we can choose. And since we do not have a way to represent negative numbers yet, this could be a way to do that. Let's take a look at the properties of the 2's complement. This is a table of the 2's complement of all 4-bit numbers. If we take a look at the 2's complement of 0, it is also 0, which is great because negative 0 is also 0. And if we look at the 2's complement of 1, it is 1111, and the 2's complement of 1111 is 1. This means that taking the 2's complement of a number twice gives us the number back, which is a great property because negating a number twice also gives us the number back. This property applies to all numbers, of course, not just 1. So from now on, we'll use the blue numbers to represent positive numbers and the red ones to represent negative numbers. Notice how the 2's complement of 1000 is also 1000. This means that we need to choose whether to use this to represent 8 or negative 8. It turns out it is more useful to use it to represent negative 8, because it makes the calculation of the overflow much simpler. So from now on we will use the 4 bits to represent the numbers from -8 to 7 instead of from 0 to 15. But what about our circuit? This is the 4-bit adder that we built previously. Now we want to change on it to make it work as both an adder and a subtractor. So let's say we want to perform A minus B. We saw earlier that we can do that by doing A plus the 2's complement of B. The first step of calculating the 2's complement is inverting the bits. So here we want to invert the bits of B. We can do that using the XOR gate. So if we look closely at the properties of the XOR gate, we realize that if we set one of the inputs to 0, then the output will be exactly the same as the second input. But if we set one of the inputs to 1, then the output will be the inverse of the second input. So if we insert XOR gates here with one of the inputs set to 1, we can invert all the bits of B. This takes care of the first step of calculating the 2's complement. The second step is adding 1. Well, remember the carry in to the first full adder that we set to 0. If we set this to 1, this will act as adding 1, which completes the calculation of the 2's complement. This right here is a 4-bit subtractor. But how can we make it work as both an adder and a subtractor? To do this, we'll need to introduce a new bit, usually called the control line. This bit holds the value 0 when we want to do addition, and the value 1 when we want to do subtraction. If we connect this bit as follows, then the inversion of the bits of B and the addition of 1, which are the steps for calculating the 2's complement of B, only happens when we want to do subtraction. Calculating the overflow here is a bit different. It is done by taking the XOR of the last 2 carry-outs. An overflow of 1 here indicates that the answer to our operation is outside the range of -8 to 7. Now this is the completed 4-bit Adder-Subtractor circuit that we built using only 3 basic building components: the AND gate, the OR gate, and the XOR gate. I hope you enjoyed this video, and thanks for watching.